there's really not anything you can do with that yet.
So Joe, not knowing the tool that you're using for that phase 2 simulation, I'm curious as to what values or parameter changes you were able to make to stay with the 9.6 control channel for your propagation versus the default code that would be on the traffic channel.
The numbers that we've gotten back, at least sort of unofficially for delay tolerance, is that on phase 2, you can do about up to 80 microseconds. But you are right. One of the issues is that you still have 9.6. You still have a phase 1 control channel, right? So that's one of the sort of gotchas about doing a phase 2 system. Our experience has been that the control channel is easier to decode for the radios than voice is. It's either an error correcting issue, or the radios can just sort of figure out, because they're sending the control channels and can sort of figure it out. So this is actually for voice, and again, because we don't actually have a lot of experience, with phase 2 systems, because there aren't really any out there, that this is sort of a swag. What our assumption here with this is that the control channel will continue to work, at least reliably enough to be able to make the voice channel at 12 kilohertz work. Now, whether that actually works out or not, we don't know yet. But that's sort of where we're going. Our experience with phase 1 systems has been there are places where the radio will decode the control channel okay, but you still don't have reliable audio. So even in today's systems.
So I'm not familiar with the control channel. Is that perhaps, does the control channel continuously repeat, if you will,
Yes.
in a frame format?
Right.
This box is this channel.
Yeah, it does, and it's not trying to reconstruct voice, right? Which is a fairly complicated. You're sending a lot of data to try to reconstruct voice. The actual information the radio has to receive to actually do a push-to-talk call is pretty limited compared to having to decode voice. So we'll have to see how it actually turns out at this point. It's like I said, it's a bit of a swag because again, they don't really have the systems out in the field that we could actually verify. But this is based on some preliminary information we've got about the modulation technique and all that. But that's where it's at. So we'll see.
So tools-wise, Joe, are the application providers making changes so you can have additional value fields to work with, or are you having to, let's say, grunt that?
Well, at this point, what we've found is that all of the propagation tools, to some degree, are a house of cards anyway, right? I mean, they're all kind of a guess. The size of your, it depends again on your terrain, but particularly in the Northwest with all the hills and the mountains and everything that we have, that it's really difficult for the tools to really accurately predict anyway. It's all kind of an average value over the area. So for our experience, we found that adding more detail, into the parameters doesn't necessarily buy you that much more in the results. Now, I would say that if we had a tool, which we don't, that was able to really model downtown areas, like the cellular guys can do, where you can model the reflections and you can do all that might be useful. But again, for most public safety and public service kind of applications, that's overkill for what you need to do anyway. Okay, so for narrowband simulcast, the result here is that the timing and overlap control is more critical. A higher degree of RF engineering is required. So that's not like your master's PhD, but more detailed RF engineering is required. And because you're going to find that trying to manage the overlaps, the thing that, and we've talked about this for years, is that people will have a non-simulcast system. They've got all high sites, right? Because they want to convert to simulcast. And so what they want to do is just convert all their high sites to simulcast. Doesn't work very well that way. And in fact, the system that we showed you here, we purposely redesigned. This was done probably 4 or 5 years ago when we did the first design on it. It was all designed with low sites just for that reason, because you could not control the simulcast overlap from high sites. Antenna and power level adjustments may need to be made after installation which is true for any simulcast system, but with narrowband, again, the overlap areas get bigger, so you have to be able to control that. And same thing as we've talked about before, you really need to have a lot of attention to detail when you're setting the system up and you're adjusting the levels. You know, just doing 1, 2, 3, 4, you know, doesn't cut it when you're setting the levels. Okay, a couple of things, again, that are not just simulcast related, but also narrowband. CTCSS decoding, we've run into some problems with some models that have a problem decoding low deviation CTCSS. You know, for every 100 hertz of CTCSS deviation you have, you're taking that 100 hertz away from voice audio. So you want to try to balance the minimum CTCSS level for reliable decoding with trying to retain as much voice audio, because that's what the user hears. And we found that some brands require 100 or 150 hertz more CTCSS deviation. So yeah, you have to watch that. Multipath fading and narrow IF response. Some of the radios that have really a pretty decent adjacent channel filtering also have narrow IFs. Well, with simulcast, it's controlled multipath, well, or semi-controlled multipath anyway. So as you drive through those multipath areas, you get fairly sharp nulls in the signal level, and those nulls can create some additional sort of audio artifacts, for lack of a better word, in your IF. The IF can actually ring a little bit, so it makes the popping noise that you get from that worse. It's less of a problem on VHF because the nulls are bigger unless you're driving at high speeds, but at 450 and 800, well, you don't do narrowband typically at 800, but at 450 you'll notice it more. Companding should be turned off. If you're using companding, so almost every manufacturer has some sort of proprietary companding approach. You should turn that off because that's done in the radio, it's not done in the system. And it's pretty easy to have low audio levels. We get a lot of complaints of people that convert to narrowband about that their audio levels are low compared to what they have. Let's see, P25 digital simulcast. Well, the delay spread tolerance is less than for analog. And you got to remember that the delay spread, which is actually your simulcast overlap tolerance, not only includes simulcast overlap, but also local multipath. So if you're in an area, canyons, mountains, even cities that have a large amount of multipath, if you're in a highly multipath area, your overlap area will be reduced because of that. Instead of just fuzzy or distorted audio, there's no audio, which is an issue for the users, because I've seen a lot of simulcast systems where there's some pretty big overlap areas and the users are able to tolerate sort of fuzzy audio in some of those areas. But with P25, there's just no audio, and the users typically don't tolerate that very well. Your voting is proprietary, so there's really no JPS or GE, or Motorola Spectrotech kind of voter that can be mixed with all different kinds of receivers and everything like there was. Phase 2 may be more tolerant than phase 1, so if you can wait, it might be worthwhile to wait until phase 2. And generally, an existing analog system cannot simply be replaced with a digital system because of the coverage changes. That's been our experience. Narrowband simulcast can be done, but it requires more care. Simulcast, again, is spectrally efficient, so if you don't have channels, sometimes you're forced into making those, buying a more expensive technology. Narrowband by itself will result in some system degradation. Make sure when you're bidding a system or implementing a system that you allow some time for adjustment after implementation, maybe even some money in there for replacing antennas or things like that, because you just never know exactly how that is, especially bad at VHF. UHF is a little more predictable. VHF, darn stuff just covers too well, and you get signal in places that you would look at and you just say, there's no way I'm getting signal from that site 35 or 40 miles away, and you are, and it can cause some problems.
Thank you, Joe.